Hi everyone, in this video we're going to start chapter 28. This is actually our final chapter of the course. Seems like we're a little early, but it's going to give us ample time to review and be prepared as we can be for the final, for test 4 and then the final exam. So this is different methods of integration in chapter 28. And section 28.1 starts out with the general power formula, and it is basically more practice with U-Substitution. So we begin with some pretty scary, ugly looking integrals, and ultimately they boil down to a power rule integral, and we'll see what that looks like in some examples. As a reminder, the general power rule looks like this. The integral of u to the n du is equal to u to the n plus 1, add 1 to the exponent, divide by the new exponent, n plus 1, plus our constant of integration. Okay, so we'll look at, let's see, 4 different examples, maybe 5 different examples using this rule. And the first one goes like this. We are going to integrate sine cubed of x times the cosine of x dx. And that integral may look a little bit scary. We haven't seen trig in an integral yet. We will for the next few sections, actually. One thing to recall, though, is this sine cubed x means the same thing as the sine of x to the third power. Okay, and that's really important to see that, because what we're going to do to evaluate this integral, where the U-substitution comes in, notice I have something to a power here, so we're going to take what's inside of that parentheses, and we're going to say, all right, we're going to let u equal the sine of x. Then the derivative of u, du, derivative of sine is cosine x times dx. The differential dx is what that is. Okay, so why is that helpful? Well, now here I have u to the third power, and the cosine x dx, that's du. So what this integral, once we make our substitution, all that we're left with is u to the third du. And hey, that's an integral we've been able to figure out for a while now. This is u to the fourth over 4 plus c, and then we back substitute. Sine to the fourth x over 4 plus our constant of integration. Boom, done. That's it. In our next example, we have to integrate 2 times the square root of 1 plus tan theta times secant squared theta d theta. Boom. That's a lot. There's a lot in that integral, okay? But we can make it look a little bit better if we make a u substitution. So I'm going to take and set u equal to what's under the radical there. U is equal to 1 plus tan theta. That's a theta right there. Poorly made one. And then the derivative of u, du, derivative of 1 is 0, it's a constant. Derivative of tangent theta is secant squared theta d theta. So go back and make a little sheet of those trig derivatives and have it next to you, or maybe pull up a paper in your notes as you're doing these homework problems, because you're going to need to remember them. So what I have underlined in red is u. What's after that I now have underlined in blue is du. So we make our substitution. The constant 2 that's out in front there, I'm going to pull that further out in front of my integral. And then what's red is u. Let me make it red. U, and instead of writing the square root of u, I'm going to write it to the 1/2 power, because I know where this is heading. And everything that's underlined there in blue is du. So I'm integrating u to the 1/2 du, add 1 to the exponent, 2 times u to the 3/2, and divide by the new exponent, plus our constant c. Okay, a couple more steps just to clean this up. We'll keep our 2. We'll flip that denominator up 2/3, and we'll back substitute 1 plus tangent theta to the 3/2 power plus c. And one last step, we can write that as a nice 4/3. 1 plus tangent theta to the 3/2 power plus our constant c. And that's it. Okay, so as you can see, a little review of U-substitution. We're doing a little integration involving trig, but you're not actually integrating any trig functions. You're differentiating. You're doing the derivative of the trig function through our U-substitution. In our next example, we're integrating the natural log of x divided by x with respect to x, all right? Now, our u here, it's not immediately as obvious because there's nothing grouped in a parentheses, there's no square root, nothing to a power, but we're going to take and set u equal to the natural log of x. Again, that's not immediately obvious, but you know the derivative of ln x, so that maybe can kind of push you in the right direction. And if you do recall the derivative of the natural log of x, it is 1 over x dx, okay? And that's what makes this substitution work. What I'm boxing in the numerator is u. Well, actually, let me box the u. And then what I'm circling, the x in the denominator times dx, the x in the denominator times dx, that's du. So when we make our substitution, all that's left behind in the integral is the box, which is u, and the sideways circle there, oval, which is du. So it's just the integral of u du. What is that? U to the first power is u squared over 2 plus c. Oh, that's it. Back substitute, don't forget that. This is the natural log of x squared over 2 plus our constant c. Done. This last one that we're going to look at here is a little bit scarier still. And as soon as you see, and I'm going to highlight it, that inverse sign to the -1, that's the inverse sign. If you encounter it in a homework problem, you definitely should go back and look at section 27.3. That's where we covered this for the first time, and I think a lot of people have forgotten these or didn't catch it quite the first time. So go back and look at that. These are their own unique derivatives. This isn't a power rule. I'm going to write something that's wrong. I'm not going to bring -1 sine to the -2. That is completely wrong. I'm just going to undo that like it never existed. Okay, so go back and look at that section. These have their own special derivatives. All right, and then the other thing that makes this challenging, even though I have something grouped in the under the radical there, that is not what I set u equal to, because I know these derivatives. I remember how they work. I'm going to set u equal to the inverse sine of x, and then du, its derivative, is all that stuff in the denominator, 1 over radical 1 minus x squared dx. Okay, that's the derivative of inverse sine. So that's why you should go back and look at that section and look at the table of the derivatives when you get to this homework. All right, so then let's make our substitution. The integral, I'll come back. Notice there's bounds here. I didn't mention them yet. I'll come back to those in just a minute. U is in the numerator, and then that stuff that is also in the integral is my du. So this, all that's left in our integral is the integral of u times du. That's it, okay? Everything else was subbed out. Okay, because this one has bounds now, I'm going to treat it a little bit differently. My bottom bound is 0, and so you can use your calculators to help you out with this. If you take your U-substitution, u is equal to the inverse sine of 0. Well, that's just 0. I know it, and my calculator told it to me. So my bottom bound stays 0. Also got to check our top bound, see what our new top bound is, the inverse sine of 0.5 or 1/2, and check that one in your calculator, and it'll say one of two things. It'll say 30 degrees, or I'm going to use pi over 6. Pi over 6 is the inverse sine of 1/2, and so that's my new top bound. Whoops, pi over 6. Okay. All right, again, use your calculator to rewrite those bounds perfectly fine. So now we can evaluate our integral, u squared over 2. I'm not going to write plus c because it's a definite integral. I have bounds on the top and bottom to plug in. Top bound pi over 6 squared over 2 minus the bottom bound is 0, so that's not going to give me much there, over 2. So this ends up being, when all is said and done, pi squared in the numerator, and 36 times 2 is 72 in the denominator. Okay, so that's the last one. That one's a little bit more challenging. But if you have questions on this, if there's something that was confusing, please shoot me an email. Let me know what's going on so I can give you a hand figuring it out. And if you run into problems on the homework, let me know that as well. Thank you for listening. Have a great day.